Hi there students, this is our video lecture for the course ENSC106, and in this video presentation we'll have a brief discussion about the course contents, the descriptions, also the topics, as well as the grading systems and requirements. We'll run through that, but of course you can find the full contents in the course syllabus. Okay, so here we have our course code, that's ENSC106, and the course title is Mechanics of Deformable Bodies. In other universities and colleges, you might find that instead of having this title, they have, like, for example, strength of materials, or sometimes they have mechanics of materials. Okay, mechanics of materials. But for us here, we use this this one, the mechanics of deformable bodies. Okay, so from the word itself, deformable bodies, if you compare that to the previous courses that you have already dealt, I mean mechanics courses, the statics and dynamics, they they both deal with rigid bodies. Okay, and for us here, we'll be doing deformable bodies. Although the word deformable bodies could also refer to, this can refer to actually fluids or solids. Solids or fluids. Because again, when we say deformable bodies, in the context of mechanics, they can actually refer to either solids or fluids. Okay, so that's why sometimes, to be more precise, that should be mechanics of deformable solids, or I mean, to be more technical, sometimes it's referred to as mechanics of elastic solids or things like that. Anyway, let's just move on. So for the prerequisites, we have ENSC 105, and the credit, we have 3 units. I mean, this course is a 3-unit course, and the number of hours is 5 hours per week. Okay, so that's our allotted time. And for the course description, we have this fundamentals of stress and strains, and actually loaded members. Okay, also the beam deflections and things like that. Okay, so for the course contents, um, first we'll talk about them. We will devote ourselves to the review of static concepts. So this will take around 8 hours, or the time allotted for this topic is 8 hours. And when I say 8 hours, that includes the lectures, the sample problems, uh, plus the time that you work on with your assignments. Okay, so that's it. Okay, so we have to have a solid foundation, regarding these static concepts. Okay, and recall that when you studied the engineering statics, uh, we talk about equilibrium. Okay, and basically, when you say equilibrium, it's a condition where the body is not accelerating. And why does it not accelerate? Is simply because the sum of the forces acting on that body is just equal to zero. And not just forces, but also the sum of the moments. Okay, so acting on a body is just equal to zero. So probably we have forces like here, like this, and we also have moments and things like that. Okay, so if the resultant force is zero, then there's gonna be no acceleration. Why? Because the of this expression, from the Euler's equation, or uh, usually referred to as the Newton's second law. Okay, although Euler's made it more rigorous, in terms of solving the equation or using the equations. Okay, so if the summation is zero, then we have no acceleration. Okay, so we need this. We need to have a solid foundations regarding the equilibrium concepts, because when we talk about strength of materials, we're actually dealing with stresses and strains which are internal. Okay, so for example, what I'm talking about is, for example, we have this bar, and we load this bar in, let's say, in tension. Okay, so because it is loaded in tension, then um, there's gonna be, if we want to check, if we want to cut a section right here, okay, what we'll see is internal forces. Okay, so let's say we'll view this side. Okay, so what we have here are internal forces. Okay, so this one is external. Okay, so let's write it here. This one is external, and this one is internal. Okay, so if we talk about internal forces, it can be, okay, so let me write it here. We have external forces. If we apply external forces in a body, then what we get is generation of internal forces. Internal forces. And when we talk about the force distribution, then that's what we call stresses. And if we talk about deformation, then that's what we refer to as, or that's related to the concept of strains. Okay, so force, internal force distributions, and then deformations, that's about strains. So if you can see that we really need to be able to determine this, okay, by applying the equilibrium equations. Okay, so external forces acting, and then the support reactions generated, and then if we cut a section, we apply the equilibrium equations, then what's going to be the internal forces. Okay, so that's why we really need to have a solid foundation on these static concepts. And so after that, we'll talk about the fundamentals of stress and strains. So just a brief overview, um, okay, brief, or let's say a little more detailed overview about this stress and strains. Also, uh, after that, we'll talk about the stresses and strains, what in members that are actually loaded. Okay, and also what if members are loaded in direct shear, or torsional members or flexural members. Okay, so what's going to be the stresses and strains. All right, so um, that's why we have this. Um, let's say this will take, or the time allotted is 5 hours. That's 1 week. Okay, 1 week also for torsional members, and we also have flexural members, right? And if you notice here, for the flexural members, we have part one and part two, and that's simply because the topic of flexural loadings, they have a lot of um, topics, like, for example, the moment of inertia. We have to have a solid foundation, or we have to review again our the topic about moment of inertia, and centroids, and also the shear and moment diagrams. Okay, so plus also the internal loads for these flexural members, they're not just moments, they're not just internal moments, but also uh, there's gonna be shear. Okay, so that's why it takes part one and part two. Then after that, there should be another topic right here in between these two topics. There should be a topic about combined stresses. Okay, so what if the the member is loaded in, it has actual loadings, plus it has also loadings that causes torsions or flexures. Then how do we compute for the stresses? Okay, so that's why we need to include this combined stresses, because in reality there could be just more than one. Okay, so another, or the next topic after this, is the stress transformation. Okay, so it's all about rotating the infinitesimal element uh, of a body, and then we'll check the stresses. Okay, and after that we'll have detailed discussions about the beam deflections, the column buckling, thermal stresses, plus also right here there should be, let's say, stresses uh, in cylindrical vessels. Okay, cylindrical vessels. Okay, so I guess that's the content of the course. And for the grading systems, we have homeworks, term exams, and projects. So for the homeworks, it's total homeworks will be 42%, and the term exams, that's 40%, and the project is 18%, and the total is 100. Now for the project, it just included here a brief the description of the project, and it's about the compilation of solved problems. Okay, some detailed discussions or detailed instructions about the project will be given soon. And for the course policy, just refer to our course syllabus. There's a lengthy section about the course policy. So regarding term exams, absences, and things like that. And for the solution guidelines, okay, so that's a separate document, and it talks about the or how the homework output should look like. Okay, so that it talks about the presentation of solutions and also the scanning um, scanning issues. Okay, and all what I mean basically it has this concept or this principle of three C's. Okay, the three C's of the solution guidelines. So number one, it should be clean, and then number two, it should be clear, and then number three, it must be complete. Okay, and when we say clean, that means that there's no erasures. Okay, and scanning issues, or let's say it should be scanned properly. And when you say clear, that means that um, solution makes sense. Okay, solution makes sense. So otherwise, if the solution doesn't make any sense, probably due to copying or I don't know, that means there's gonna be deductions regarding this. I mean deduction because of this criteria. So it's not clear. So how could you, for example, you have answers, you have a final answer, but the solution doesn't make any sense. So how come you arrived in a correct answer even though the solution is mathematically wrong or things like that? So there'll be deductions for that. Okay, so, and when we say complete, it means that there should be line labels in the solution, line labels, and there should be figures, okay, complete figures in the solutions and things like that. Okay, so that's our course policy. So you can read the detailed contents of this in our solution guideline documents. Okay, so I guess that's all. And in our next video, we'll be discussing our first topic on the review of static concepts.